special subject. And the subject of today is, you guess it already, quantum. Is it 0 or 1? So Monday is the quantum day. Oh, very difficult. So I will start with a tutorial, because typically we start with a tutorial. The tutorial will be about quantum, but about the bad side of quantum. Yeah, post-quantum security. Right? It will be, if you think last year was difficult to follow the quantum gravity, this year will be really difficult. I promise. But my intent, can you hear me in the back? Or do you have a microphone? My intent is not that you follow everything, because we have a paper on that one. If you really want to read it, there are 50 pages of mathematics behind it. You only should get an impression. You only should get an impression of how hard and difficult it is, what is the machinery behind it. That is excellent. Sorry, sir, I think it's fine. It's fine. It's fine. Then, after the break, we have Stefan Werner here. Some of you know him. This is the third visit to Crete. It's because of quantum computing, not because of Crete. He told me, right? He hates to come to Crete. It's too long and so on, right? Then we have Magdalena Hauser and Wolfgang Lechner. I didn't see them already. So they run a company called Parity QC. And they are discussing the technology, what they are doing, the latest advancement. They are partnering with another quantum computing vendor. Then I'm pleased to have Michael Furch here. Michael Furch is running a quantum computing company that builds a photonic quantum computer. But he will tell us also, here's Michael, yeah? But he will also speak about what doesn't work, is quantum real ready. So he's skeptical, and he and I will have fights about that, right? So. And then we have the poster session, right, where we present the papers, 3 papers every day. And as typical, we don't have question and answer session because we have the posters on Friday where you can discuss with the people what they did present in a more relaxing way. What I don't know is, where's Timis? We have a Uso reception tonight. And I don't know, do you know where it is? Is it down at the beach bar? Do you know that? Okay. Johanna, the Uso reception is down the way. Where is it? She finds out. This is okay. So then the reception, welcome reception starts at 8:30, and Johanna will let you know where it basically is. Right? We had it in the past at the Café Neo with a very nice view, but for some reason they changed it to the beach bar because it's easier to serve drinks and so on, right? And then you are off to have dinner. Right?
Beach bar, but it's 7, not at 6:30.
Oh, beach bar at 7. Okay. Okay, beach bar at 7. Tonight. Yeah, are you invited? No, Wolfgang told me, typical in history is, Wolfgang and I always fight. And then in his presentation, he pays me everything back. And he told me this morning over breakfast, I have nothing nasty to say. I say, I will make sure that you have enough nasty to say. This was a mistake he made. Okay. So, now we stop here, and we go to post-quantum security. So, here's a paper that Johanna and I have written. It's still on archive and under review in the journal. It's 50 plus pages on the mathematics, the machinery behind. Is it not clear enough? Get it?
It's not sharp.
Not sharp. Okay, so here's the QR code. If you scan it, right, then you can read it. And of course, the slides are after the talk. Most speakers, as me, give the slides to Themis, and then they'll be uploaded, and the same is true for videos, right? Themis is taking videos about the talks. If you are a speaker that does not want to have a video taken, let Themis know, right? By default, we take the videos of the talks, and I know that a couple of people really look it up on YouTube. So what I'm going to do is, I explain to you what is classical encryption and what the hell does it have to do with something called discrete logarithms. Sounds great, discrete logarithms. Then I will show you very briefly, because most of you understand quantum computing, right, because I was speaking about it for a couple of years, what is the underpinnings of quantum computing and why can Shor solve discrete logarithms and how fast can it be. And then I'm diving into something that's called lattice-based cryptography, but this is the rescue after Shor, right, what can be done. And then I present two algorithms in more detail called the lithium and Kyber, which are algorithms that have been standardized by the National Institute of Standards. Then I explain to you what some industry people are doing, and I work with a company called WSO2, and we put all their products quantum safe. So we spend some effort to make products quantum safe, and then the summary. So what the hell is classical encryption and discrete logarithms? This is the famous RSA algorithm. This is the underpinning of today's cryptography, right? Asymmetric. So what you do is, how does it work? You pick two prime numbers, it's important. Large prime numbers, you compute their product. You compute the product by each prime number has been diminished by 1, which is called the Euler function. Then you choose your secret key. It's a small number, so that this number phi of n is co-prime to g. That means g and phi of n have greatest common divisor of 1. So, next, to determine the solution d of the following equation. D times my secret key g should be congruent 1 modulo phi of n. This is a very fast algorithm based on Euclid's algorithm, right? So solving this equation is easy, and this solution d and the large and the number n is the public key, and g is your private key. You destroy p and q and phi of n, and then the whole machinery works, as you know. Then if you have a message, what do? The message is mapped to its binary representation, and the assumption is that mu is less than n. If it's not less than n, you split mu into parts so that each part is less than n. Then you compute mu bar, which is mu, one of the message part, to the power of d. D is part of the public key, modulo n, n is part of the public key. This is then the encrypted message. How do you decrypt it? Okay, you take the message that you received, mu bar, you take the power of g, g is your private key, take it modulo n, part of the public key, and then you have the decrypted message. Sounds very easy, and it is easy, a little bit of mathematics, right? And cracking your private key means to determine phi of n, because d is part of the public key, n is known. What about phi of n? If you know phi of n, then you can determine the secret key, because solving this equation is simple, and phi of n is simple to be computed if you know n, which is the product of p and q. If you could factorize the n, which is part of the public key, then you could crack the secret key. So, and this factorization is, in fact, as I will show in the next couple of slides, to compute a discrete logarithm. Right? Here's an example, not my own, from the original RSA paper. You take two prime numbers, p and q, you multiply them, then you take phi of n, which means you reduce the prime numbers by 1 and multiply them, which is this one. Then you choose your secret key. Now you need to feel around a little bit, and here this is really a good secret key because they are co-prime. Then you solve this equation. Solving this equation, you get d 17, so the public key is 17, plus this number. There is a 9 too much. And then you have a text, it's all Greek to me. It has not been invented here for Greek, but it is from the original paper. It's all Greek to me. You encode it. For example, each letter is mapped to a number. A is mapped to 1, B is mapped to 2, Z is mapped to 26, blank is 0, 0. And the black block representation of this message is 0, 9 for I, 20 for T, and so on. Each of the blocks that I've chosen is less than the number n. Right? Now I compute the first block 0, 9, 20 to the power of 17. Part of the public key, modulo, part of the public key. Here the 9 is wrong. And then you get this number out, and so the overall encrypted message is this. And if you then perform what I said before, you decrypt it, you take 948 to the power of your secret key, 157, modulo the part of public key, which is IT, and so on. So it's quite simple and quite efficient, right? So it works very nicely. So what the hell does it have to do with logarithms? First I need to explain what it has to do with an exponential function. So you take a number a, an arbitrary number a, assumed to be less than n, then you define a map, the exponential function, that takes the number a to the power of the argument x modulo n, yeah? And this is then the module exponential function with basis a. And this exponential function very often is periodic, like the sine, like trigonometric, like the sine function and so on. And it has a period p if and only if x at argument p is x equal 0, and p must be minimal. So exponential function is periodic. That means if I substitute p here in this equation, then a to the power of p modulo n is a to the power of 0 modulo n, and a to the power of 0 is 1 modulo n. And that is, you write it differently, that says a to the power of p is congruent 1 modulo n. That means that there is a number k, so that k times n is a to the power of p minus n. So x has the period p if this equation holds, right? And for most simple condition, you know that exponential function is periodic. So assume that I know the period of the exponential function. So if I know it, then I know that a to the power of p is 1 modulo n. That means there's a k, so that a to the power of p minus 1 is k times n. Next, we assume that the period is even. If the period is not even but odd, then you choose another a. And you can prove in number theory that in more than 50% of all cases it is even. So if it isn't, you can use binomial formula. That means a to the power of p minus 1 is a to the power of pi by 2 minus 1, pi by 2 plus 1. That means this term and n have a common divisor, or this term and n have a common divisor. Especially the greatest common divisor of this and n, or this and n, is a divisor of n itself. That means if we can determine the period of the exponential function, then you can determine a divisor of n and iteratively define the prime numbers. That means factorization means to determine the period of this damn exponential function, this numerical exponential function. Convincing. And cracking key means again determine phi of n, d is known, and then solving this equation, which is simple, and so on and so on. So if you can factorize n, which means you can determine the period of x1, then you can crack keys. And as usual, the exponential function has an inverse function, because the logarithm function, right? The so-called discrete logarithm, right? xa of x is a to the power of x modulo n. The smallest number y such that a to the power of y equals z modulo n is called the discrete logarithm, and you write it log z equals y. It's a number theoretic function. It assigns to each natural number another natural number, and as usual, the exponential of the logarithm is the identity and vice versa. For example, we know that 2 to the power of 4 is 16. If you compute it, you find out it's congruent 5 modulo 11, because if you divide 16 by 11, 5 is the remainder. That means the logarithm of 5 to the basis of 2 is 4, right? And we know that the exponential function has the period p if and only if a to the power of p is congruent 1 modulo n. And 1, yeah, that means in order to determine p, I need to compute the logarithm of 1 to the basis of p. And because if I have the period, I can crack the number, I can find the prime number, I can find the factorization. We now should have seen that factorization can be reduced to compute discrete logarithms. Right? So if I have an algorithm that computes discrete logarithm, I can crack any number. I can factorize any number. But you all know there's another kind of encryption, right? It's elliptic curves. Is this secure? What the hell are elliptic curves? Here's an elliptic curve. An elliptic curve has this structure, right? satisfying this condition. This condition sounds very weird, but it means that the curve doesn't intersect, there are no cusps, so there are no singularities, as mathematicians say, right? So if you satisfy this condition, then no singularities is there. And obviously, because here is y squared equals something, the curve is symmetric to the x-axis, as we see in this nice picture here. And what you do is, if you have a point P, then you reflect P across the x-axis and you denote it by pi minus 1, P minus 1. It's again a point on the curve. And then you can define an automatic operation of the curve, right? It's a multiplication. It assigns to 2 points another point on the curve. If you take the red points, P and Q, you connect the red points and the line intersects with the curve, then you reflect the point that you have, and then you get the product of P times Q. Right? Very simple. If you have a point P like the blue one, if you only want to square P, you take the tangent of P at the curve, find the intersection, reflect it, and this is P squared. And if it happens that you have a point, the tangent of which does not intersect, you add an infinite point E to it. Right? This is an infinite point E, and then this is E squared. E is P squared. And it turns out that this E is the neutral element of multiplication. That means P times E equals P, which then means it's not simple but cumbersome to prove it's a commutative group. So each elliptic curve is a commutative group. Right? You can do math with it. And this is the basis of elliptic curve cryptography. So what people are doing is they standardize the parameters A and B because the computational properties depend significantly on the values of the parameters, right? And crypto guys, they know what are good A's and B's. Then you determine a so-called generator. It's an arbitrary chosen key that you choose and publish. And each participant has a private key, and the private key S like secret, and G to the power of S then is the public key of you. And cracking and this is a game. I mean, if I can compute S by taking the logarithm, then I can crack elliptic curves. That means cracking elliptic curve cryptography also means to compute discrete logarithms. Seems to be a powerful tool, this discrete logarithm. And now the shock comes. We didn't discuss Shor, but Shor algorithm can break ECC much easier than factorizer. You need much fewer qubits, much less operations. So elliptic curve is much more under jeopardy than prime numbers. Right? And in the end also we'll always find the corresponding links. Very briefly, how does it work? Elliptic curve, Diffie-Hellman. Diffie-Hellman is something that is used in order to establish a session key, right? A symmetric key. You use public-private key, asymmetric encryption, to exchange a secret key, to agree on a secret key. This is Diffie-Hellman. And Diffie-Hellman, in the meantime, is often used for key exchange. So G is the generator of the curve. Alice has this as a public key. SA is the secret key. G to the power of SA is her public key. And Bob has a secret key SB, G to the power of SB is his public key. Alice and Bob simply exchange PA and PB. That means the generator to the power of their secret key. Alice computes this value. She received PB, takes it to the power of her private key. The same is done by Bob. And then you find out that this number KA equals KB. That means immediately they have a session key, a symmetric key that they can use to control the exchange of information. Right, so very easy. And then I said it can be cracked. Why they can be cracked? So for those of you who are a bit more familiar with quantum, this is how a repetition, right? You know that a quantum bit is in two possible states, 0 and 1 at the same time. We call that superposition. So a state is a linear combination of 0 and 1, and these alphas and betas are even complex numbers such that the squared moduli of this number equals to 1. It means a qubit is always a vector of length 1. Although I draw it this way, this is wrong because alpha and beta are complex number. This is not in R2 but in R4, in C2, in the 4-dimensional space. Right? And because we can't imagine what a four-dimensional space is, right, you can project a qubit into three-dimensional space by taking polar coordinates. So because each qubit can be represented as a point on the two-sphere in R3, and it's determined by two angles, the angle between the z-axis and the vector that represents psi. And if you project psi into the xy plane, you get this angle rho, which basically is the second argument that you have in order to represent this qubit psi. So a qubit, a bit, has always two possible values. We know that 0 or 1, right? But a quantum bit has an uncountably infinite many possible values. Right? Any point on this kind of sphere, which is called Bloch sphere, and Bloch got a Nobel Prize in physics, right? So this already indicates that the qubit is much more powerful. And an interesting philosophical thought is a qubit appears in nature everywhere. So it's simple, quote unquote simple to produce a qubit, but the bit is then complicated. In order to implement a bit, you have lectures on technical computer science. It's quite difficult to implement a bit, but a qubit is nature. And last year I told you that even space and time is a net, is a tissue of qubits. Right? Even the space we are living in, the time, if you take a look at the clock, it's all built out of qubits. So qubits are absolutely canonical, but we are miseducated to think in terms of bits. So, as a classical register, you bundle bits into a register, you can bundle qubits into a register. Very simple, it's a quantum register. It consists out of n bits, and because each qubit is a linear combination of 0 and 1, then you have at the end, if you have n qubits, you have combinations, a 2 to the power of n combination of 0, 0, 0, and so on. Right? So each quantum register is a superposition of these 2 to the power of n different states. And quantum parallelism means also classical register consists of n bits at a single value at a time. They are one of these n's here. Sorry? Yeah? Classical register is either completely 0 or everything is 1. Right? So a single value at a time. A quantum register with n qubits is a superposition of 2 to the power of n values at the same time. Right? That means quantum computer manipulates this huge number in a single step. Right? This which is called quantum parallelism. So computations of the quantum computer is parallel computing. To give you an example, if you have 50 qubits, right, you have information in the order of peta. And 50 qubit these days is a small machine. IBM has about 400 that the customers can use, but the number of atoms in the universe is less than 10 to the power of 90, which means it's less than 2 to the power of 300. It means a machine with 300 qubits. In order to simulate it, right, you need to turn each and every atom of the universe into a bit, which is obviously not possible. That means you can't really simulate computations that you can easily perform on a quantum computer. Well, it stops at 56, 57, at least with 50 qubits. So this is also quantum parallelism is an extremely powerful mechanism. And then you can entangle qubits. If you have a quantum register and you manipulate a single qubit here, that's okay, the other qubits are hanging around. But if they are somehow correlated, and I was speaking about entanglement last year extensively, they're somehow correlated, right? Then if you fiddle around with one qubit, all the others are shaken too. Right? Because they are somehow related. And the intuition, this is always what I like, this is why I need to present it, of entanglement is best, no applause for my animation. So by two dice. So I have two dice, they are somehow correlated, right? They are entangled. What I do is I can move them apart, right? I stay on Earth, you go to Mars, they can be arbitrarily far away. And if I roll my dice and I see what the result is, the phase is, immediately I know what the result of your dice at Mars is. And the astonishing thing is it happens at arbitrary distance, it's a determined state, which was an absolute shock to Einstein, who got a Nobel Prize for quantum physics and said this must be bullshit. Right? Quantum physics can't be real because you can't communicate so fast across arbitrary distances. Speed of light this is it. And last year I explained to you that many physicists in the meantime believe that they understand entanglement as wormholes in space-time. If you entangle two qubits, they build so-called nano-black holes, and then there is a wormhole between them, and the communication happens in femtosecond, which is you can't measure it. The last Nobel Prize last year was given for people who control how to measure these these short time frames. And so entanglement is very powerful, and in fact, it's unique for quantum computing. Right? You really can't simulate it. Each computation that does not involve entangled qubits can be realized in principle with the same efficiency than on a quantum computer classically. But in principle means if you have n qubits, 300 qubits, you can't. In principle, you could do that if you can turn each and every atom into a classical bit, right? So in principle, it's a theoretical result, but in practice, you can't do it. And there is a very famous theorem: every quantum algorithm showing exponential speed up compared to classical algorithm must exploit entanglement. Famous theorem from 2003. So entanglement is absolutely important for quantum computing. And how do you manipulate qubits? A qubit, as I said before, is a vector of length 1. Yeah? Alpha and beta determine the probability of being in 0 or 1 if you measure it. So that means Q is a vector of length 1. And if you manipulate a qubit in a quantum computer or a quantum register, you turn the vector of length 1 into another vector of length 1. Right? Here's a vector of length 1. If I manipulate it, I turn it to another vector of length 1. And such an operation is called a unitary map. Yeah, it's a special map in complex vector spaces. Right? So a quantum algorithm consists of a series of unitary maps or matrices. Right? Very simple. Right? You don't need to learn Pascal anymore. A little bit of complex linear algebra is easier. Right? So this is only the impression of Shor's algorithm. Right? You initialize your quantum computer in a ground state. The quantum computer, the register is split into two parts. Right? Then you apply something called the Harman transformation in order to create superposition. Then you apply a function f. F is this module exponential function, right? And at the end, after applying the oracle in quantum computing is a subroutine. You apply the subroutine on the quantum register, you have the value table of the exponential function in your quantum computer. And they are entangled, and then you apply something like the Fourier transformation, you know, that allows you to do periods of periodic functions. So apply the Fourier transform, I measure what I have here, and then I need to do a little bit of classical mathematics, continued fraction. This is Johanna 70 pages. If you want to understand this little thing here, scan this one, Johanna, and I have a paper, what that basically means here, right? So, the comparison is, the classical algorithm is the best known classical algorithm is exponential, Shor's algorithm is polylogarithmic, right, much faster. What does that mean in practice? In practice it means you have this RSA. So RSA 2048 has been created because the challenge to crack RSA 2048 means numbers, bits of which require 2048 bits. It has been chosen, the number, because you need the lifetime of the universe to crack it, right? And based on Shor's algorithm, right, if you have an error-corrected quantum computer, and error correction these days we don't have it. Companies are working on it. IBM, I follow what IBM is doing. They make progress, error mitigation, and so on, right? So based on the 1 gigahertz processor, quantum processor, you can crack RSA 20 in a couple of minutes, which is a threat. Dangerous. But you can lean back, yeah, because error-corrected computers are not around, blah, blah, blah. Lean back, rest assured. So, because even worse, if you can, there are several estimations how many qubits you basically need and how many gates you need, unitary maps you need to execute without any errors, called fidelity. In order to factorize a number that has z bits as a binary representation, To run Schwarz algorithm, you need, and the estimations differ a little bit. Here's one that says 5n plus 1 qubits and 4 times n to the power 3 operations. And such a computer is called a CRQC, a cryptographically relevant quantum computer. Right? But again, RSA 2048 requires 10,000 bits and the building of operations. And what do we have today? 400 qubits and thousands of stable operations. Rest assured, lean back. It seems to be even possible for quite some years. But then there's one, IBM published a paper that they need 24 physical qubits to realize a single logical qubit, a stable qubit. In the past, right, there have been codes published, right, that require hundreds or even thousands of physical qubits to realize a single logical qubit. So this is a significant progress towards a quite cryptographically relevant quantum computer. Because in order to realize 10,000 logical bits that I estimated on the slide before, you need about 240 physical qubits. And this may be, our roadmap said, and Stefan knows it better, end of the decade, early next decade. So expect it in a few years. I tell you what few means in an hour. And another advancement is there. There's a group that factorized a 48-bit number with 10 noisy qubits on a superconducting quantum computer. And they estimated that they need less than 400 physical qubits, but a depth of thousands, plural, of stable execution steps to crack RSA 2048. Right? And this is a NIST machine, a machine we have around today. Right? And they used an algorithm called Quava, and they executed something here in between. Right? So the qubits are there, but the number of steps that you need to perform on the machine, this is not realistic these days. But again, another approach that makes it a real threat to our society. Right? So it's getting close. We are not yet there, but it is getting damn close. And then many people said symmetric encryption is absolutely safe. And then there was a shocking paper 18 months ago, something that's called the variational quantum attack algorithm, VQAA, that is suitable for NIST machines, and they can crack symmetric keys. They did experiments on IAAS like symmetric cryptography, which invalidates two assumptions that was consensus before, namely that symmetric encryption is quantum safe. I will comment that in nearly 90 minutes. Error-corrected QPUs are needed to break encryption was also the consensus. So here's an algorithm that can even break symmetric encryption. But those who haven't heard, you can interrupt me anytime. It's a tradition, right, to interrupt and say, Frank, this is bullshit or something like that, or, oh, I like it, yeah? Just do it. So what the hell do we do? I'm not discussing that there are quantum protocols. There are protocols on a quantum computer that you can use to generate and exchange symmetric keys. Right? The BB84 and variants of it. So it's more than 40 years old, and many people are working on realizing it. Like in Europe, we have projects going on, quantum cryptography initiative. Each country is funded by the EU to experiment with infrastructures to enable this quantum safe symmetric key generation and exchange. Right? But it takes quite some time and is damn expensive, because you need either geostationary satellites where you exchange information via laser beams from one point to another, or you need extremely stable fiber channels with Verstärker, with amplifiers between, after a couple of 10 or 100 meters. So it's an enormous investment we as a society have to make in order to become secure based on quantum security. So the question is, can we do something with traditional algorithms? This is based on lattice-based cryptography. So what are the basics about, I don't have a clock, I'm just ashamed. So Joanna, 11 Uhr, schreist du, ne? Okay. What the hell is a lattice? So you take linear independent vectors, v1 to vk, and take an integer linear combination. So the coefficients g are integers. And then, if you, this is V2, this is V1, if you take integer linear combination, you get what is called a lattice. In German, it's not Verband, sondern Gitter. Yeah, this is a lattice. And you can easily prove this is a subgroup of Rn, it's commutative, right? Because here addition is commutative and so on. It's very simple. And an equivalent definition that we need in shortly after the break is that the lattice is a discrete additive subgroup. We already know that it is an additive subgroup, and discrete means that for each 2 points in the lattice, there is a number epsilon, so that for each 2 points in the lattice, their distance is always bigger than epsilon. So it's discrete, that's what you imagine what discrete is. Right? And you can add 2 lattice points. So from a high level, this is obvious compared to the definition I had before, because Zn is a lattice, right? And it's obviously additive, and it is discrete. Discrete is not so simple to prove. If I take a regular matrix, right, and I take a look at the solution, at the n times x, and x is a point in the lattice, this is a lattice again, and then I can take, because m times x can be rewritten as this one, and then you see immediately this is a lattice where the columns of the matrix are the basis of the lattice. And based on the above, what I say here is, if you have a regular matrix, a matrix determinant of which is not 0, right, then the solutions of n times x equals 0 is a lattice again. And this is what we need when I explain to you what is learning with errors. Learning with errors. So, each lattice has a basis. Why the hell is lattice-based security complicated? Because the lattice has many different bases. It has a very nice basis, the blue one, it's an orthogonal basis, and it has a strange basis, the red one. How do I measure the badness of a basis? Very simple. You take a matrix, the determinant of which is 0, is 1 or minus 1, which is called a unimodular matrix. Then you have a nice matrix, if you have a basis, B1 to Bn of your lattice, and B is the matrix with the columns of the basis B1 to Bn, then you can compute column C1 to Cn of matrix C, which is B times U, and this is also a basis. Right? And computations in the blue, the nice basis, are simple, much more simpler than in the red basis, especially if you have high dimensions. In quantum cryptography, we talk about vector spaces of high dimensions, right? And I give you, and now we want to find out how do we determine, how do we measure whether a matrix is computationally simple or complicated. So, this is the notion of a nearly orthogonal basis. If you have a basis the matrix built by the basis, then the determinant of this matrix is the volume of the parallel epipet spanned by the vectors. If they would be orthogonal, then I would multiply the length of the cuboid, right? This then here is the volume of the cuboid, but the determinant, if they are not orthogonal, is always less. So parallel epipet has a volume that is always less than the corresponding cuboid. Right? That means if I take the quotient, this is the volume of the cuboid built out of the vectors, and this is the volume of the parallel epipet spanned by them. This is the orthogonality defect. Right? Because this term is 1 if the basis is orthogonal, and otherwise it's always bigger than 1 because the determinant is always less than the volume of the cuboid. Right, so we have a measure, I will show you an example that this is the right measure, and the lattice reduction problem is to determine the basis with a minimal defect, and is known, this so-called lattice reduction problem is NP half. And this is one of the underpinnings why we rely on lattice-based cryptography to build an infrastructure that is quantum safe. Here's an example. I have a good basis. I have a lattice that is spanned by the unit vector and the vector of length 2 on the x-axis, and I have a bad basis. Right? This is a nice bad basis. Right? There are bases where you even don't see that there are different vectors here. So the orthogonality defect of G is 1 because it's an orthogonal basis, and of the bad basis is 31. 31, okay, there are bad bases that are in the order of billions, right? And then I take the vector V, and the vector V is this vector, it's outside of the lattice, and I want to find the closest point in the lattice closest to V. Because we will see, you encrypt in practice messages as points in the lattice, as points in vector space, and then you need to approximate a point closest to the encrypted message, not to crack it. We'll get clear. So if I take the good basis, this is the good basis, I need to solve this equation, 4.5, 3.5, this is this V, I compute it, I get this out, but because I want to have a point on the lattice, I round it, because x and y are not integers, I round them to 2 and to 3, and then I substitute it here, and then I find the vector 4, 3, which is the blue one that is an approximation of V. And admittedly, it's damn close to V. If I choose the bad basis and perform the same computation, right, you get a vector, this red star here, which is absolutely not close to the green thing. So computation, because of rounding effects, makes it bad. So it is a bad basis, and what we do is your secret key is a good basis, and the public key is a bad basis. Nobody can basically crack it. Before continuing, before continuing with some more example, I need to introduce a few problems. The shortest vector problem is to determine the vector x star that is the shortest vector in the lattice. Right? It has minimum length. And you can prove it's NP hard if you take Euclidean norm, and it's NP complete if you take the maximum norm. Strange, but it depends on the norm, right? So finding the shortest vector in the lattice is cumbersome to do. And then there's a very crazy name, shortest independent vector. Shortest independent vector does the following. It takes a basis, computes the length of the basis vector, and takes the minimum. So, and then you want to find one basis, the maximum length is minimum over all the different bases. It's called the shortest independent vectors problem. And this, what a surprise, the SIVP short vector is also NP complete. And the closest vector problem is you have a vector W, and you want to find the lattice point x star that is closest to W, and this is also NP complete, the closest vector problem. So we have found problems like closest vector problem, shortest independent vector, NP complete, lattice reduction, finding a good basis is NP hard, and I only mentioned that Shor's algorithm is BQP. BQP is the complexity class that is, so to speak, the P of classical computing. Right? And in quantum computing, you always look for algorithms that are BQP, because then they have success amplification. If you execute such an algorithm a couple of times, you know that you will get a precise result. So BQP algorithms are very nice. And another thing is, why the hell do we think that factorization is simple? Because if I pick a random number, right, it is even. With 50% it is even, I know immediately a point vector. Why the hell do theoreticians say that it's complicated? Well, it's complicated because it is worst case hard. Right? There is a problem that is really hard, but if you pick an arbitrary problem, an arbitrary number, you don't know is it really hard. In theory, what we would like to have in security is something that's called average case hard. Average case hard means pick any number, and this should be damn hard. Right? And this short, and we will see one lattice problem that is average case hard, and you can reduce all the other lattice problems to this average case hard problem. Right? All the lattice-based algorithms are average case hard, which is what I basically said. Right? And as of now, we don't know whether cracking keys is P or NP. Right? This is an open problem, and you don't know whether it's average case hard, even if you reduce the odd numbers. Right? Nobody has proven that cracking key is that prime factorization is average case hard. It's not reverse case hard, it's an open problem. But we want to have average case hardness, ideally. And now we need to introduce something. Ja, wie viele Minuten haben wir noch? 5, super. Yeah? Learning with errors. What the hell does this mean? I take something, a ring. A ring is nearly a field like the real numbers and complex numbers, but it turns out that some of the numbers don't have a multiplicative inverse. It's a ring. You can do very nice computations. So if you take a finite ring, and you will see we have finite rings in post-quantum cryptography later on, you take vectors over this vector space over the ring, so to speak, and you take numbers out of the ring, then assume you have a function that is unknown, it's a linear function, and the f of the vector ai is roughly ti. That means it's ti but with a small error. And the learning with error problem says, determine this unknown function f based on training pairs. ai is the vector, ti is this rough result here, right? So this is learning with errors. This is the problem. If you reformulate it, you will choose fixed s. You have a chosen fixed s. It's a secret message, the secret. And you pick uniformly random small elements, the errors, e1 to en. You compute the vector ai, the vectors you have taken here, times the secret s. You add a little error to it, plus ei, this is this ti. And then you say you have the vector ai and this here computed vectors, test data. This is the test data and you should recover the secret, right? The message that got encrypted. This is the idea behind dilithium and Kyber, the two standards that are out. And you can reformulate it as an equation system, because if I take the vectors that I've chosen, a1 to an, and take this, each vector as a column, I have a matrix. Then I take a vector, which is the t. E is a vector that consists of the errors. And the LWE, learning with error problem, is to find a solution S of this linear equation A times S plus E equals T. Right? This is exactly the slide before, right? You can immediately see that here. These are the T's. And if you multiply the columns AI with the vector S, right, and add this is exactly this thing here. If you have no errors, that means E is 0, A times X equals T is solved in polynomial time. It's Gaussian elimination. But if you have little errors, the problem turns out to be very hard. Interesting. And if, now it is a deep theorem, if the learn with error problem could be solved efficiently, then the shortest vector problem, which is NP hard, can be solved polynomial time with a quantum algorithm. Right? But approximation is assumed to be hard, so the LWE problem should be hard. And all known algorithms we have today to solve this learning with error problem are exponential. All known today. I will come back to that later. The shortest integer problem means if you have a matrix that consists out of integers only, and integers between 0 and q minus 1, zq is a ring where you have addition and multiplication modulo q. Q is a prime number, right? You have this kind of a matrix, and you are looking for an integer solution, the solutions of which are small, less than beta, right? You have the so-called shortest integer solution problem, SISP, right? And shortest integer vector, the shortest independent vector problem can be reduced to this SISP, to the shortest integer solution problem, and the randomly selected lattice problem is as hard as this worst case thing. And now, if you think it was complicated, this was the easy part, right? So, I promised you, you will hate me. What are polynomials? We all know what polynomials are, but I just say it briefly. Right? A polynomial over a ring R is this kind of a string, right? X is considered to be a variable, right? This is a polynomial. You can add two polynomials, right, by adding the coefficients of the potentials of the powers of this variable. You can multiply them right? This is a formula of multiplication. Or equivalently, a polynomial is a sequence where only a finite number of which are not 0, right? And then adding two polynomials means to add the sequence element. Multiplying polynomials means to multiply a subset of the elements of and so on. The details are irrelevant only because computation with polynomials can be reduced to computations over sequences. And now we are not taking polynomials over an arbitrary ring, but polynomials over this strange ring ZQ, which is the numbers from 0 to q minus 1, and you add and multiply them by taking the residue, dividing them by q. So each message is represented as a bit string, B0 to Bn. These are 0 or 1. And the polynomial determined by the message is then the corresponding polynomials where the coefficients are 0 or 1, the 0 or 1s that are coming from the message. So the coefficients of this polynomial are 0 or 1, they are small, and what you are now doing is you scale them, you stretch them a little bit. You take q, divide them by 2 and take the smallest integer close to q. If you take this times n, then the coefficients are either 0 or this larger number than 1. Right? Now if you multiply or add polynomials, you need to multiply and or add the coefficients of the polynomials. That means the coefficients become large, especially if the degree n of the polynomials, this n, are large. But a message has a lot of bits. That means the polynomials have a huge degree. That means if you multiply and add them, their coefficients will get enormously large. And this means manipulating polynomials becomes inefficient. The solution is you take the computations modulo q for prime number, and this is the reason why we use polynomials in post-quantum computing later over this finite ring. Yeah, because then it's more efficient. But polynomials and their degrees get large too if you multiply them. Right? The polynomials, you multiply the degree of the polynomials. That means we also would like to limit the degree of polynomials, and what do? We take residue classes of polynomials. Even more complicated. Remember analysis, partial integration, where you need to compute residue division of polynomials. Yeah? Complicated. And what can you do? You take the analog of prime numbers in the space of polynomials, which is an irreducible polynomial, which is a polynomial that cannot be written as a product of two non-constant polynomials. Here's an example. This is an irreducible polynomial in z of x, but it's not irreducible over the real numbers, because if you have real numbers, you can write x squared minus 2 as this expression. And that means we take residue classes, we take a polynomial f, and all the polynomials we have here are taken as residue classes of this polynomial f. And if f has a degree n, then all polynomials g in this set of residue classes have a degree less than n minus 1, because zq has a cardinality of q, and I have the degree f are the polynomials, combinations of these numbers. This is a finite ring consisting out of q times degree f numbers. Right? That means after you multiplied and added polynomials, you perform polynomial division. And the remainder of the polynomials is the result of the operation, and this controls the computational complexity that we have. Right? It's a finite ring. This is a reminder, so that you don't kill me when I leave the door. Now, what is polynomial division? Here's a polynomial, and I want to divide this polynomial with this polynomial. How do you do that? Well, you need to find out what do I need to add here. So if I multiply this, the white space, with this x, results in x squared. Right? So it is obviously x. Then I multiply x with this polynomial x minus 2. Right? I do that and prepare the subtraction here, like written division that you do. I compute it, and then I subtract, I compute the difference, and what is left over is 3x. Then I take the minus 6, right? -6, I get it from above. Then the question is again, what is needed here in this white space? So if I multiply this with x, gets 3x, and you know it, it's 3, because if I do the same, right, then I get this here, and then I have 0. It means the remainder of this division is 0, right? Well, this is 0, whatever here. Another example, you can have an integer number here, right? Or you can, of course, even have a polynomial. The remainder would be this one, right? So the result of this division here, this is the residue classes of this polynomial in the ring that is the residue class of x squared plus 1. So it gets even more complicated, yeah, because I'm not taking this residue class of polynomials, I take a vector space consisting of the residue classes of the polynomials, right? Because if I want to increase the security level of my cryptographic mechanism, that in this learning with error problems, right, it requires, so increasing the security level means to increase the degree of the polynomials. And I don't want to increase the degree of the polynomials because the computation effort is high. To avoid this, you don't increase the degree of f, but you take a polynomial with a small degree, it's 256 by the way, and you substitute it by the vector space, quote unquote. So I take it times k, the Cartesian product of this set of residue classes of polynomials. This has the advantage that the degree of polynomial is not reduced, but the algebraic structure of this piece is not a vector space that I said, it's a module. A module is nearly a vector space, but it's a vector space where you substitute the field, real numbers, complex numbers, by a ring. It sounds, why is it so bad? Because it behaves completely differently. For example, you don't have a basis in general, right? Modules don't have a basis. If you have a basis, you can have an arbitrary, you can have different, if you have two bases, they could have different cardinality, so you can't define what the dimension really is, right? That means increasing security level in post-quantum, right? It requires to increase k, but the degree f can be kept the same, right? So the significant effort is not significantly increased. This is now something that we call algebraic lattice cryptography, right? Because if R is a ring, R to the power of k is a module, right? Addition is component-wise. This piece is a module, even a finite module. This is the number of elements you have in this finite module. One ramification is, in order to solve a lattice problem, in this kind of a module you need a norm. Shortest vector problem means to compute the length of something. Right? What we do is we map this polynomial, the residue class of polynomial, to tuples, and this is obviously a vector. This thing is part of, is a subset of z to the power of k. Z to the power of k is a vector space, and here you can compute norms. Right? So what I said is this algebraic structure has a norm so that we can speak about shortest vectors and so on. The situation, 1 meter and then we have the break, is we are not dealing with lattices and vector spaces, but in modules, right? And the points in this module are not tuples of numbers, these are tuples of polynomials. Right? A very strange algebraic structure. Right? In Chiral, that we will discuss after the break, the prime number is this one. In dilithium, the prime number is this one. Multiplication of polynomials are based on something that I don't understand as number theoretic transfer. There's a library that is fast in order to manipulate polynomials. So it's not a vector space, a lattice, the points of which are tuples of polynomials. And then do a computation. Damn complicated. And we continue. So the last terminology, if you use only a ring, it's called regular learning with error problem. Ring learning with error problem is if you use this special ring in module LWE, this is what post-quantum cryptography is lattices in this piece. And now we deserve a coffee. Yeah? Okay. So this was the hardest part. Yeah? Okay. Just to make sure that some of you come back. We're going to